Good morning students. Today is lecture 31 under module 11. In today's lecture we will cover liquid membranes. So, liquid membranes are very interesting. If you recall, during the introduction class I told you that any membrane which is made up of liquid is a liquid membrane. So, they are very interesting. They have lots of positive features for which the researchers' attention has been drawn to this particular technology. And we will discuss about the concept that different types of liquid membrane, how to prepare liquid membrane, then how mass transfer happens in liquid membrane, then there are applications. I will show you one case study also, the work which was carried out in my own lab. So, let us begin. A liquid membrane is as I told you that it is nothing but the membrane itself is a liquid. So, the concept of solid membranes was extended to include membranes made up of liquid stuff such as oil or even water or any other organic solvents. The material for the preparation of a membrane need not be a solid only. A liquid phase existing either in supported or unsupported form. We will see and learn what is the meaning of supported and unsupported, that serves as a membrane barrier between two phases of aqueous solutions and gas mixtures. Now, let me try to explain you by showing that how we can prepare a liquid membrane in a very simple way, maybe in the lab. Okay. So, most of you have seen the YouTube manometers which are used to measure pressure readings. Okay. So, let us say something like that. We have a YouTube manometer. Okay. Right. This is the simplest the form which I am trying to actually draw, right, the simplest that we can make it in the lab itself, and something like this. So, it has two limbs basically. So, you pour your membrane which is of liquid either water or oil or any organic solvent into one of the limbs. So, okay, then it will come down and settle down here. Okay. So, let us say it comes and settle here. Right. So, this is your liquid membrane part. So, basically here, okay. So, this is your liquid membrane part, right. So, now there is a limb 1 here, this is limb 2 here. So, in the limb 1 you will have your feed, you can pass on your feed here, okay. And here you will have an extract phase. Please understand that there is a extract phase here, this is something extra which is not present in other membrane systems. Okay. So, this phase will basically extract the materials which we want to remove from the feed phase. Then let us say in the feed phase the solutes are there, we want to remove, the solutes will travel through this liquid membrane and will come to this phase. Okay. Now, extract phase will be chosen in such a way that this will trap these solutes which we want to remove from the feed phase and will not allow the back diffusion, to happen. Otherwise, it will happen that again they will transport from here to feed size, and after some time you are seeing that again you are back to the original state. So, that this should not happen. So, this is how you can prepare a liquid membrane in the simplest way. Now, the liquid is a separation barrier between two phases or medium where the transport occurs by the solution diffusion mechanism. The mechanism of transport is solution diffusion. In general, liquids have large diffusion coefficients compared to polymers, and for certain gases they can have enormous solubility. Now, but a liquid film lacks mechanical strength. So, this is one of the most important disadvantages of this liquid membranes. As such, an appropriate technique has to be adopted to stabilize the liquid membrane so that it does not get ruptured during its use. And membrane defined as is the barrier which separates two phases and restrict transport of various chemicals in a selective manner. Now, advantages are liquid membranes are highly selective. As I told in the beginning of this lecture that I can actually target and make a liquid membrane which will remove and separate the solute which we want to separate from the feed phase. So, they are very highly selective. Then we can have different modes of transport also, not only restricted to solution diffusion, we can have carrier mediated transport where a particular group or carrier will help to remove the component more efficiently than that of the usual liquid membrane without having a carrier. Now, it does not require an energy, so appreciable energy savings, environmentally benign, clean technology with operational ease, it is easy to operate, replaces the conventional process like filtration and distillation, ion exchange and chemical treatment systems, okay. Produces high quality products, greater flexibility in designing systems. With the use of carriers, this is what I was just telling, specific molecular recognition can be achieved, and disadvantage is stability. Now, the uses are there are manifold uses: fractionation of hydrocarbons, recovery and enrichment of heavy metal ions such as copper and mercury, removal of trace contaminants from wastewater, biochemical and biomedical field applications, membrane reactor incorporating simultaneous separation and reaction process. So, let us now compare the liquid membrane with other membranes. So, unlike solid polymeric membrane, liquid surfactant membranes do not develop pinholes because of the surface tension effect associated with the surface film of liquid surfactant and do not have to be replaced or repaired. So, this is one of the biggest advantage. Then due to the absence of pinholes, no possibility of clogging of the membrane and therefore constant filtration rate. So, there is no question of any concentration polarization that is happening as in the case of solid membranes. So, possible to provide much greater surface area for mass transfer within a given process volume. Liquid membranes are much thinner than the commonly available solid polymeric membranes. So, the film resistance is low. See, this is also another advantage, and no film like problem. Liquid membranes are formed almost instantly and they recovered after use. So, let us now try to understand the different types of liquid membranes. Basically, we can categorize them into three different types. One is BLM, which is bulk liquid membrane. Second is ELM, which is emulsion liquid membrane, which has a lot of practical applications. Then the third is immobilized or supported liquid membrane. Now, immobilization or supported liquid membrane has come into picture basically to increase the mechanical stability of the membrane, right. So, the most of the liquid membranes, their mechanical stability is very poor. So, to improve it, it was thought that liquid, the membrane which is liquid will be impregnated inside a porous support. So, it may be another porous membrane inside which you will immobilize the liquid membrane, and this porous membrane or support will provide the mechanical stability to the membrane. So, in this way those are either called as immobilized liquid membrane or supported liquid membrane. So, lot of applications are there. So, the mechanical strength has actually increased by making supported liquid membranes or immobilized liquid membranes. Well, let us say one by one. So, this is BLM, this is the most simplest of one, which I was just showed you in the first slide itself, drawing a YouTube manometer in how we can convert it to a liquid membrane setup. Here you can see there is a, it's a glass beaker, you can call, this is a beaker type of thing. Okay. In which we can put two different, these are partition we can call it, okay, made up of usually glass, okay, and then your organic membrane containing carrier or whatever, without carrier also does not matter, containing carrier or no carrier also, okay. So, this is your part where your liquid membrane part is being fixed. Then there is a receiving phase here, okay. So, this side and this side, this is receiving phase, okay, and this is from where you are entering your feed phase. So, there is a magnetic stirrer which is rotating, okay, to just enhance the rate of mass transfer, right. So, this is a typical BLM setup. Now, the membrane phase is usually mixed intensively, so that the diffusion path is limited to the distance of the boundary layer. This is very important. So, in this case of transport of substances from aqueous solution, the membrane is an organic phase of density different than that of the water phases. A U-tube cell is used, some type of carrier is placed at the bottom of the tube, that is the organic membrane phase. And now, two aqueous phases are placed in the arms of a U-tube floating on the top of the organic membrane with a magnetic stirrer rotating at a fairly slow speed, okay, in the range of 100 to 300 rpm. The transported amounts of materials are determined by the concentrations in the receiving phase. So, stability is maintained as long as the stirrer is not spinning too quickly, otherwise the liquid membrane will break. Now, these BLMs or the bulk liquid membranes do not have any commercial applications. There is in the lab scale to generate data or to characterize a particular liquid membrane that was developed. So, then the next one is emulsion liquid membrane. Now, emulsion liquid membrane is a liquid phase that separates two miscible liquid phases across it. Okay. Now, thus the liquid membrane should be immiscible in the two liquid phases being separated. So, liquid membrane phase should be in such a way that there are two miscible liquid phases in between one immiscible membrane phase. Okay. Now, the type of liquid membrane, either water or oil, will therefore depend upon that liquid phases, either oil or water being separated. Okay. Usually it is oil water type applications, basically oil water separations. Okay. So, water and oil if mixed vigorously, emulsion droplets are formed. Emulsions are stabilized further by addition of some surfactants. Macro emulsions are of the size of 0.2 to 50 micron, micro is 0.01 to 0.2 micron. Micro emulsions more stable because the interfacial tension is negligible. This is just a schematic representation to try to understand. Let us try to understand what is this. So, here whatever it is here, these are continuous phase. Okay, outside this emulsions. So, this hatched portion what you are seeing is the membrane phase, and whatever is the small bubbles you are seeing, this is this one, these all these are all internal phase, or we can call it as receiving phase. Okay. We can call it extract phase or extract phase. Now, you are understanding. So, this is your continuous phase or feed phase. Okay. This is the hatching portion. Okay. So, this is all your membrane phase, right, and inside that there is a internal phase. You can visualize at a bubble within a bubble. This is looking like, na, it is a big bubble and there are so many small bubbles. Exactly it looks like this. If you take it take the emulsions and put it under a microscope and see, it just look like this. So, the innermost bubble is the receiving phase, and the outer bubble is the separation or skin containing the carriers. Anything outside the bubble is the source phase or your feed phase. Okay. Now, different types of ELMs are there, usually 3 or 4 distinct types. The first one is oil in water emulsion. So, here water is continuous phase while the oil is the discrete phase. Then second is water in oil emulsion. So, here oil is continuous phase and the water is discrete phase. Then third one is water in oil in water. So, here water and oil emulsion acts as the discrete phase and water acts as the continuous phase. Another is the reverse of this, oil in water in oil. So, here oil and water emulsion act as the discrete phase and oil acts as the continuous phase. So, this is the emulsion liquid membrane schematic setup. You can see how actually you will from this you can understand that how ELMs are prepared. Let us see here. So, this is the first chamber which is emulsification. Here your aqueous stripping phase, okay, and liquid membrane phase are mixed together, right, and then they will form something like this, okay, just what we have seen. This is what will be formed here. Then you add your feed phase here. Okay. So, then there is discrete phase. So, basically this is what is there here. Now, this goes to the extraction process. So, you just stir it little with very low agitation speed. Okay. Sorry, this is not the feed phase, the feed phase is coming here. So, this is what is present here. You are putting your feed phase here and slowly stirring it. During that your mass transfer will takes place and the components or the solutes which you want to transport from the feed phase to that of the receiving phase will travel through the emulsion membrane phase and eventually it will get inside or trapped inside the receiving phase, okay. So, or stripping phase, whatever it is you come. So, once that is done, then you leave it to a settling tank where the treated wastewater will be collected at the bottom and the oil rich phase will be collected and it will be sent into a de-emulsifier. So, this is a de-emulsifier, okay. So, this is emulsifier, this is de-emulsifier. Here you are making emulsions, here you are breaking emulsions. Okay. So, whatever you break it, then you got the extract phase here, the same receiving phase. Basically, what is done here? This is breaked into this plus this. Okay. So, two different phases. One is the membrane phase, okay, and this is the extract phase, right. So, you can take the extract phase and again put it here, right. Stripping phase and the liquid membrane phase is being recycled to the main stage. So, this is how it happens. So, in industry there are so many emulsifiers, then de-emulsifiers, so various settling tanks, okay, mostly in series, they operate in series. Okay. So, the formation of emulsions has certain limitations. So, factors affecting emulsion stability must be controlled. So, this is very important. So, these factors are ionic strength and pH. So, in case during the separation the membrane loses its stability, then the separation achieved to that point is completely destroyed. So, this is one of the biggest disadvantage of these ELM membranes. So, in case let us say the separation is happening, almost 30-40% separation is done and the next stage you would have got 60 to 70% or your desired separation. In case the emulsions breaks, then you are just back to the starting point. So, After the separation, there is a need to break the emulsion to recover the receiving phase and to replenish the carrier phase. Now, this is a difficult task, as in order to make the emulsion stable, you have to work against the ease of breaking in break it down, because many times you are supplying stabilizing agents such as certain surfactants to increase its mechanical strength. Now, you want to break it. So, you are going against the entire forces of whatever is present to break it down. So, it is a tough task basically. So, next one is immobilized or supported liquid membrane. It is either you can call it ILMs or SLMs. Now, in this case the liquid is filled inside the micropores of a solid porous polymeric membrane, just like this. Let us assume this is a microporous support, okay, and these are the pores, these pores are filled with the liquid membrane. It is very easy to do it in the lab actually. So, the porous membrane provides mechanical support to the liquid membrane, thereby addressing the issue of stability of the liquid membranes to certain extent. Now, ILM, SLM can be easily prepared by impregnating the liquid, that is the membrane phase, usually organic, inside the pores of a porous membrane, usually hydrophobic. Now, once you have the impregnation membrane, so how do you do it? You take a this one, let us say microporous membrane, microfiltration membrane basically of 0.45 micron pore size or any pore size that is actually required. Okay. Then what you do basically, you can take it in a petri dish, put the microporous support on that, and over that you just pour the membrane phase, the liquid membrane phase. It is either oil or any other organic solvent over it. So, slowly by gravity what will happen, the pores will get filled. Okay. So, this is a lengthy process, or what we do in the labs basically, we put the microporous support in a vacuum filtration unit and then slowly and then pour the liquid membrane phase over the surface of the membrane on the microporous support, and gradually very slowly just switch on your vacuum filtration unit, and in a controlled manner you have to do it, very low pressure, otherwise it will suck everything and all the membrane phase will come to the permeate side. So, that should not happen. So, once it is done, then you can take it out, wipe it the membrane surface, so that the extra liquid membrane phase whatever is present on the top surface of the membrane has to be wiped out. Okay. Then you either you can go for dry it or no need of drying also, you can just take it and use it. So, you use it something like this. Okay. So, you can have a, let us say some sort of cell system, okay, right. So, here you can have your liquid membrane here. So, this is liquid membrane. So, you stir it, one is feed, one is your receiving or extract phase. Okay. So, we are stirring both sides just to enhance the rate of mass transfer. From here also the components should move to the liquid phase, and once they come here they also should be properly trapped inside the receiving phase. So, there are different types of supported liquid membranes. Thin sheet supported liquid membranes. So, thin sheet supported liquid membrane is just a porous polymer membrane whose pores are filled with the organic liquid and carrier set in between a particular source phase and the receiving phase, which are being gently stirred, just whatever we discussed. So, it can be utilized for laboratory scale, but cannot be scaled up for industrial use. That is another thing for this type of thin sheet supported liquid membrane. Okay. So, hollow fiber supported liquid membrane. Now, we have discussed a lot about hollow fiber, its different types of properties, how it is used in different applications. So, here also we can have hollow fiber supported liquid membranes. So, the design of the hollow fiber supported liquid membrane closely resembles to a large electrical cable. So, in this membrane system, the outer shell is a single non-porous material and through which the materials cannot be transported inside. So, here you can see the membranes, this is the membrane porous support, right. These are holes basically, inside which you have the liquid membrane impregnated. Okay. Feed is being passed from this side, okay, and receiving phase is outside. So, what will happen, whatever it is the solute is coming here, it will be transported through this and will go to the receiving phase, will be transported through this liquid membrane phase and will go to the receiving phase. This is how it works. So, inside the cell there are many thin fibers running the length of the cell. So, the source phase is piped through the system from top to bottom, and the pores in the fiber themselves are filled with the organic phase. Now, the carriers in that phase then transport source across the receiving phase, and then the receiving phase is forced out through the sides of the wall. So, let us now understand the comparison between the three different types of liquid membranes, bulk, emulsion and immobilized. So, bulk liquid membranes are not widely used in industry mainly due to the small contact area of the membrane with other phases and very slow process kinetic. In emulsion liquid membrane, there is huge surface area creation for mass transfer. This is the biggest advantage of emulsion liquid membrane, and extraction and stripping are achieved simultaneously. In a single step, both extraction and stripping are going on. Okay, in a single operation like the conventional solvent extraction. And in immobilized and supported liquid membrane system including the hollow fiber systems, the surface area and the membrane thickness provide rapid transportation. The source or receiving phases are more easily recoverable than the emulsion system. The entire source and receiving phase are not in contact with the membrane at any given time. Instant leakage and contamination are easily handled. Now, let us try to understand the mechanism of mass transfer in liquid membranes. In all types of liquid membranes mentioned earlier, the transport mechanism is the same, and according to the film model of mass transfer, it can be divided into the following steps. The first is that diffusion through the boundary layer in the feed solution. Okay. Then sorption on the feed solution or liquid membrane interface. So, basically if you try to explain it, let us say this is a emulsion in which there are receiving phases and this is the membrane, right. So, this is receiving phase, this is membrane phase and this is your feed phase. Now, what will happen? There will be a thin boundary layer here. Okay. So, what will happen? Initially the solute will diffuse through the boundary layer from the bulk to the boundary layer. Okay. So, here once it comes here, then it comes to this place which is the feed solution liquid membrane interface. Okay. It will diffuse through this, then the boundary layer and on the feed side, then transport in the membrane side. Okay. Then once it reaches here, it got transported in the, this is all membrane side, it transported to the membrane side, that is convective transport basically. Once diffusion through the membrane is happening, then it will reach to the diffusion through the boundary layer on the receiving side. So, there is some thin boundary layer here, then it gets transported and it reaches here, it will diffuse through this boundary layer and then it will get inside the receiving phase. So, desorption on the membrane or receiving solution interface, diffusion through the boundary layer in the receiving solution. This is how it happens for all different types of liquid membranes. So, broadly speaking, two different types of separation mechanisms can be proposed for mass transfer in liquid membranes. So, these are simple permeation which is due to diffusive transport and then facilitated transport mechanism. Now, let us understand the simple permeation mechanism. Now, since a liquid surfactant membrane is a thin film or liquid either oil or aqueous phase composed of surfactants and their solvents between a feed or receiving phase, any immiscible liquid can serve as a membrane between the two liquid and gas phases containing a solute at different concentration. So, basically we are talking about a ELM here. Okay. So, if the soluble in the membrane phase and has a reasonable diffusivity through the membrane, then its selective transport through the membrane from higher to lower concentration side may be achieved. So, higher the solubility and the diffusion coefficient of the solute, more efficient will be the separation. Hence, the product of these two physical properties is a measure of the permeability of the solute through the membrane. This type of permeation is not of much technical importance and is suitable only for studies on emulsion stability, just for lab scale studies basically, because in industrial parlance where you need continuous separation, we need a higher permeability and separation. So, this is not going to help us. So, next is facilitated or carrier mediated transport mechanism. So, in this type the effectiveness of separation through a liquid membrane is improved by maximizing the flux through the membrane phase and the capacity for diffusing species in the receiving phase. Now, this we can do it by two distinct different mechanisms. The first one, let us understand, is uncoupled transport. Now, here what is happening? Now, extract and solute diffusion through the membrane phase to the inner phase. Either the extract which we want to remove or the solute will diffuse through the membrane phase to the inner phase. Now, extract should be soluble in the membrane phase, that is very important. At internal phase boundary, extract will react with the reactant in the inner phase and forms a complex which is insoluble in the membrane phase. Now, counter diffusion is restricted. No reaction terms are involved in this type of reaction. One classic example is phenol and caustic solution separation using paraffin. So, this is uncoupled transport. So, nothing is getting coupled together. Okay. And the second is coupled transport. So, here an agent is used to transfer extract from outer to inner phase called a carrier. There is a third component which is added, okay, to the membrane phase. So, extract is insoluble in the membrane phase, carrier reacts with it at outer boundary to form a complex, okay, which is soluble in the membrane phase, otherwise it will not transport or diffuse inside the membrane phase. Carrier is present only in membrane phase, complex diffuses towards the inner boundary where it exchanges the extract ion with the reactant present in the discontinuous phase. The carrier becomes free, it will again diffuses back. One classic example is mercury removal using oleic acid as a carrier. So, there are many such examples actually of coupled and uncoupled transport. So, this is how actually it is happening. So, two components are often involved in a carrier mediated transport known as coupled transport. Okay. So, component A and component B, right. So, here two types of coupled transport are considered. First is co-coupled transport, second is counter-coupled transport. In co-coupled transport, two components are moving in the same direction. Okay. So, means A and B both are diffusing in the same direction, and in counter coupled transport, two couples are moving in the opposite direction. So, just it is being shown here. So, A is moving here in this direction, B is moving in counterclockwise direction. Okay. So, when it comes here, okay, so it is the A is bound to the carrier which forms a complex AC, then it transports to the membrane phase, and once it comes to this side, it will release the A and the C is back. Now, simultaneously the C is getting bound to the B also. So, BC will again diffuse from the BC complex will diffuse from this inside the membrane phase, we will release the B, we will get a B here and the C is again going back. So, this is how the counter coupled transport happens. So, the basic feature of carrier mediated transport is that the complexation reaction must be reversible, otherwise transport will stop once all the carrier molecules have formed a complex with the solute, right. Do you get it? So, if there is no carrier molecule free to bind with the solute, then there will be no more separation, it will reach some sort of equilibrium. So, the affinity between the carrier and the solute may vary appreciably. Thus, a strong complex, that is one exhibiting a high affinity between the complex and the solute, may result in a slow release, while a weak complex, that is one exhibiting a low affinity between the solute and the carrier, could mean that only limited facilitation occurs, so that the selectivity is also very small. So, let us understand the transport of oxygen and nitrogen. The oxygen and nitrogen fluxes through a water film, only water, okay, with and without the presence of a carrier are depicted. So, this is a flux versus the feed pressure data. So, the carrier in this case is as a cobalt compound. This carrier molecule forms a complex with oxygen, but not with nitrogen. So, this is oxygen specific carrier. So, it will form cobalt oxide basically with oxygen, but it will not react with nitrogen. So, the solubility of oxygen in water is always greater than that of nitrogen, and consequently a higher flux is obtained, which is enhanced in the presence of a carrier molecule. So, already the solubility of oxygen is higher in water than that of the nitrogen. So, it will diffuse very fast, but with the presence of a specific carrier, the flux will increase further. So, some oxygen molecules are transported by the carrier and others are transported by ordinary molecular diffusion or free diffusion. So, please remember that even if there is a carrier presence, it is not that only the carrier mediated transport is happening. There are some molecular diffusion or ordinary diffusion transport is also happening without the carrier. Now, this facilitated effect is greater at lower oxygen partial pressures, because the carrier will be saturated at higher oxygen partial pressure or concentration. So, you can see the flux is high with oxygen with carrier, oxygen without a carrier, then nitrogen with and without carrier is the same, because nitrogen is not reacting with the carrier. Okay. So, this figure tells us that what is the importance of a specific carrier mediated transport. So, ions are of interest in facilitated transport, because a large number of complexing agents are available as carrier molecules, especially for ion exchange components. Now, an example of coupled transport is the transport of nitrate ion. Now, to remove nitrate anion from a dilute solution via a coupled transport mechanism, the other component must have a lower affinity for the carrier in comparison to nitrate, otherwise it will try to bind to the carrier. Okay. But this must not be too low, otherwise decomplexation becomes very difficult. So, the chloride appears to be a good component for exchange with nitrate. So, you just see this how it is happening. So, nitrate in phase 1 or feed, this is phase 1, phase 2, okay, is exchanged by chlorine, whereas chloride in the phase 2 is exchanged by nitrate. Okay. So, the nitrate anion is transported against its own driving force, with the actual driving force in this process being the large concentration difference in chloride ions across the membranes. Now, please try to understand this, what is happening. Though nitrate is having a concentration difference or concentration gradient, however, that is not helping. What is helping is the chloride ions concentration difference between two sides, that is the driving force, okay, because nitrate is binding to the chlorides. So, affinity between nitrate ion and the carrier is much higher relative to the chloride ion. Decomplexation in phase 2 can occur when a very high chloride concentration is maintained. Equilibrium reaction is RCl plus nitrate equals to RNO3 plus Cl minus. Okay. So, this is how the counter current transport is happening. You can just have a look here. Okay. So, this is the entire liquid membrane phase. Okay. This is feed phase and here it is the stripping phase. Let us now try to understand the different components of a liquid membrane. The different components are surfactant, emulsion and carrier. Now, if at all carriers are present, it is not mandatory. Okay. So, surfactants is a substance which migrates towards the interface and modifies the interface behavior. We have already discussed a little about surfactant when we have discussed MEUF or here micellar enhanced ultrafiltration. So, the action of surfactants, the desired property of a surfactant is that it should have a very low CMC. Okay. So, non-ionic surfactants have very low CMC values as compared to ionic. Ionic surfactants will have CMC about 1 to 10 to the power of minus 10 grams per liter, whereas non-ionic surfactants will be 10 to the power of minus 4 grams per liter. So, once the interface becomes saturated, the surfactant molecules get oriented in the bulk of liquid in such a way to minimize the force of repulsion. Thus, they form micelles. We have already discussed this. You can see that how micelle is forming in a hydrophilic medium, this is in a hydrophobic medium. You can see in hydrophilic medium the heads are inside the micelles, okay, and in hydrophobic medium the tails are joined each other. It is not joined exactly, some sort of interaction is happening, okay. And this is in hydrophilic medium micelle, this is in hydrophobic medium, and this is about your surface tension versus surfactant concentration. You can see this is your critical micellar concentrations. This we have already discussed, just to again make you understand easily without going back to the earlier lecture. So, the role of surfactant is to reduce the interfacial tension, reduce the amount of mechanical work that is needed to create extra surface. A surfactant stabilize emulsion by forming mechanical and electrical barrier around particles. Now, relationship of surfactant structure to emulsifying behavior. Now, by changing size and structure of hydrophobic group, change the hydrophobic behavior of the surfactant, right. Similarly, change hydrophilic groups also. Hydrophilic lipophilic balance is very important, it is called HLB. Then depending upon this balance, surfactant activity is scaled. For purely hydrophilic material, HLB number is assigned as 20. For purely hydrophobic material, HLB is 0. Surfactants have HLB number anything between 0 and 20, and HLB number can be determined by experiments or calculated using some formula. Now carrier. Now carrier is concentrated in the membrane phase, it should be dissolved in the membrane phase, reacts with the extract molecule at membrane continuous phase boundary, form complex. Now this complex diffuses through the membrane phase to the inner discontinuous phase boundary. It exchanges extract molecule with discontinuous phase by virtue of the concentration difference again. Now selection of carrier is very important parameter, which carrier to be chosen. Now it should be soluble in the liquid membrane, it should be non-reactive and immiscible with raffinate phase, okay, or your extract phase. So otherwise it will try to dissolve or get into inside the extract phase. So readily react with the extract at continuous phase boundary, readily exchange it to the discrete phase boundary, should not react with the membrane phase. So these are some of the properties of the carrier, so which one need to take into account when you are choosing a carrier. So factors influencing the separation. So for example, hydrocarbon separation, toluene and N-heptane. So based on this particular example, it is discussed actually how the different factors are influencing the separation. So effect of contact time between the solvent and emulsion. So always in any separation, you know, or any mass transfer that is happening or even reaction that is happening, contact time is extremely important. So contact time should be optimized, it should not be too less, it should not be too high, okay, there should be some optimized value. So which needs to be find out by doing different experiments. So separation factor increases to a maximum with increasing contact time and then decreases again. So at the start of contact, unequal distribution of large emulsion aggregates in the mixture. As contact time increases and the emulsion aggregates become better distributed, mass transfer rate increases. With further contact, because the amount of the less permeate N-heptane in the emulsion phase becomes larger. Some parts of the membrane become unstable and break, and separation factor decreases. So, effect of the relative amount of the solvent. So, separation factor increases to a maximum and then decreases with increasing K. For low values of K, emulsion aggregates coils, mass transfer area is small, K increases for the overall concentration driving force becomes small. Okay. So, the next is effect of the volume ratio of the surfactant solution. So, as emulsion breakage decreases, membrane becomes thick and stability of emulsion increases. Now, at R above 0.4, no further increase in the emulsion stability will be noticed. So, then effect of surfactant concentration, high emulsion breakage at concentration of 0.1% decreases abruptly when concentration increases up to 1% and decreases slowly above 1%. Separation factor increases to a maximum and then decreases at concentration above 1%. Effect of mixing intensity, this also plays a very important role. Permeation rate increases with increasing mixing intensity. With increase in agitation speed, emulsion aggregates become smaller and well dispersed. Beyond certain rate, emulsion cannot withstand the high mechanical forces and begins to break at higher speed. Now, let us now discuss the different applications of liquid membrane. The unsupported liquid membrane has been used for removal of phenols and ammonia from wastewater, and extensive experimental investigations have been carried out. Removal of these contaminants from wastewater is dictated by environmental constraints, and there is an incentive to reduce the cost of water treatment, which is usually carried out biologically, although resin adsorption can be used for removal of phenol. Separation and recovery of copper, zinc, nickel, precious metals, rare earth metals, alkali metals, etc. from aqueous solution using LM have been studied extensively. So, phenol removal. Phenol and its derivatives are toxic and represent frequently found pollutants in surface and tap water and in wastewaters coming from various production processes like refinery, metal finishing industries. Phenol is hugely present. So, an industrial plant for phenol removal from wastewater was built in China at the end of 1980s. So, this plant is capable of treating 0.5 ton per hour of solution with a phenol concentration of 100 milligrams per liter, 100 ppm. So, important parameters are surfactant concentration, sodium hydroxide concentration in the internal phase. Sodium hydroxide is the stripping phase that will finally take the phenol inside it and will trap it, and it will make sodium phenolate basically. So, then volume ratio of liquid membrane phase to the internal phase, mixing intensity, temperature, type of organic solvent, stabilizer addition, solute concentration in the external phase. So, these are the parameters which is actually all optimized for this particular plant. So, results is that a significant result of this screening was that the increase in phenol removal efficiency with the increase in surfactant concentration up to a certain value. So, it has been seen that you keep on increasing the surfactant concentration here. So, your phenol removal percentage is happening up to, let us say, 91 here, okay, then it decreases, right. So, it is increasing, then it decreases further here, okay. So, up to 8 we can say it is fine, right. So, 91% phenol can be removed in a single stage process, 99.8% result achieved by using a two stage process. So, another example is zinc removal. So, zinc ion is used to improve weave during spinning. So, in the production of artificial silk. So, this ion is washed away during fiber ringing and is removed with wastewater. Zinc is highly toxic. So, in 1986, ELM method was successfully commercialized for the first time to remove zinc from wastewater in the viscose fiber industries at Lenzing AG in Austria, in a plant that can treat up to 75 meter cube per hour of zinc bearing wastewater. Now, this plant was capable of removing zinc very selectively, okay, from a concentration of about 200 to 300, huge concentration, 200 to 300 ppm, corresponding to a zinc removal efficiency of greater than 99.5%. 3 other ELM based industrial plants for zinc removal are also working. So, they are at Glanzstoff in Austria with a capacity of 700 meter cube per hour, CFK Schwarz at Germany with a capacity of 200 meter cube per hour, and Axo Ede in Netherlands with a capacity of 200 meter cube per hour. So, then next one is cadmium removal. So, cadmium is found in industrial liquid coming from different industries such as manufacturing of cadmium nickel batteries, pigments, coatings, phosphate fertilizers and electroplating industries. In 2010, approximately 85% of cadmium compound, mainly a sulphide and oxide and hydroxide, have been used in the production of cadmium nickel batteries. So, as a result of the high toxicity of cadmium, which can cause dangerous environmental impact as it affects both the aquatic as well as human life, removal of cadmium was done with ELM, and TOA, that is trioctylamine, was used as the mobile carrier. So, the results that is obtained are the optimum concentration of surfactant was found to be 3%. Okay, for this particular application, de-emulsifier 0.4 molar was used to maintain the stability. The removal efficiency increased with carrier concentration. So, as the concentration, carrier concentration is increased from 0.02 to 0.04, you see the removal efficiency increased from 70% to 99%. So, excellent removal is obtained. Then another case is arsenic removal. Arsenic is a big menace in some of the Asian countries, especially Indo-Bangladesh border. So, water contamination with harmful arsenic compounds represents one of the most serious calamities of the last 2 centuries. Natural occurrence of the toxic metal has been revealed recently for 21 current countries. Worldwide, the risk of arsenic intoxication particularly high in Bangladesh, India and European countries. So, results is that the best result on the recovery of arsenic 3 corresponding to a recovery of above 95% was obtained by adopting the following operational conditions. Internal phase is 2 molar potassium hydroxide, membrane phase is 6% volume by volume, L113A, this is a particular organic component, and 4% by volume liquid paraffin. External phase is 4 ppm arsenic 3 and 7 am hydrochloric acid, 7 molar hydrochloric acid. Phase ratio is 2 oil into 3 internal and 1 emulsions to 5 water. Agitation speed is almost 400 rotations per minute, and 10 minutes is the extraction time that was given. Okay. So, another case is bisphenol A is an endocrine disrupting chemical, is an important chemical used principally as a monomer in the production of polycarbonates, epoxy resins and other plastics. It is very it's a big nuisance in the baby feeding bottles actually, for which there is a hue and a lot of hue and cry. So, it is non-biodegradable and resistant to chemical degradation. It has been detected both in industrial wastewaters and in surface waters at concentration levels that are of environmental concerns, because it represents a risk to humans and wildlife. Das and Hamarawi in 2010 studied the extraction of BPA from aqueous solution using an ELM. So, the effects of the main experimental conditions affecting the stability of the prepared oil water emulsion are surfactant concentration, emulsification time, internal phase concentration, volume ratio of the internal phase to the organic phase. 98% removal was observed with excellent emulsion stability. So, very quickly I will show you one of the case study which was done by one of my PhD students, Dr. Santhiraju Pilli. So, what he has done is that he has removed endocrine disrupting chemical, here it is endosulfan, okay, from wastewater using a ionic liquid based supported liquid membrane. Okay. Now, let us quickly go through. So, endosulfide is highly toxic. Okay. So, it is staggering, trouble in it creates staggering, trouble in breathing, vomiting, gastrointestinal tumors, hyperactivity, tremors, convulsions, lack of coordination and unconsciousness if you are continuously being exposed to endosulfan. And you can see this time weighted average and short term exposure levels is very high. So, human poisoning incident is already reported. The lowest reported dose that caused death is 35 milligrams per kg of body weight. So, you can understand that this is highly toxic. So, what we did is actually we took actually ionic liquids as one of the component of the membrane phase. Basically, the membrane phase is ionic liquid. So, ionic liquids are very interesting solvents. They are actually salts made up of one cationic group, one anionic groups. We can choose a particular cation and choose a particular anion, fuse them together, you will get an ionic liquid. So, at room temperature, there are room temperature ionic liquids which are called actually RTIL. Okay, room temperature ionic liquids. So, they are liquid at room temperature. Okay. So, we have used mostly RTILs. So, there are n number of ionic liquids available both commercially as well as you can prepare. So, which ionic liquids to choose for our particular application. So, that is why we have done some theoretical calculations. I will not go into detail about this. So, we used one Cosmo-RS model. Okay, this based on activity coefficient, thermodynamic concept actually, and you find out the selectivity using this equation, right. So, what you get is something like this. Okay. So, these are selectivities values at infinite dilution and ambient temperature for imidazolium, pyridinium, ionic liquid with alpha endosulfan. Okay. So, you can see then whichever is best, let us say this is best here in this particular case, in this particular case let us say this is best, you take this ionic liquids. See, if this is not commercially available, then we have gone for the next one, which is the next selective, highest selective one, okay, or whose selectivity is the second highest, okay, and see if it is available commercially, then take it. So, this is how we have done some theoretical calculation. So, let us anyway not go into that. So, applications of Cosmo RS as pre-selecting tool for ionic liquid for removal of EDCs. It's ILs found which are exposed to dissolved EDCs better than commonly used ILs. The smaller the value of the activity coefficient, the stronger is the interaction between the solute and the ionic liquid. 984 possible ionic liquids we have screened. So, this is done using simulation, okay, here theoretical screening. So, this is the selectivity order. The TBP is one particular ionic liquid is the highest, followed by TIBMP and so on. So, since we do not have a these ionic liquids available commercially, so we have gone for the C4DMIM PF6 was chosen for our experiment. It is a imidazolium based ionic liquid with hexafluorophosphate as the ion. So, this is your cationic group, this is your anionic group. Okay. So, then we have to prepare the supported ionic liquid membrane. So, we have prepared, as I have just told you in few slides before, how to prepare supported ionic liquid membrane. So, then you have to measure the flux, okay, using this equation minus V by A dC by D8 rate of permeation. Okay. Let us see how it has been prepared, done the experiments. So, SLM experiment. So, we have a magnetic stirrer, a plate something like this. Okay. Then what? Then we have clamps fixed into that magnetic stirrer. Then we have two different cells, glass cells. So, you can see this is one glass cell here which has come here. Okay. Then we have placed the supported ionic liquid membrane to the mouth of the glass, the first glass chamber, let us say the glass chamber 1. Okay. Then another glass chamber comes. So, let us see this is glass chamber 2. Okay. Then it is fitted and clamped to the setup. Okay. So, we have transferred the feed phase here and we have transferred the receiving phase here. So, feed phase is endosulfan in aqueous medium and stripping phase is your sodium hydroxide. Okay. Then it will be stirred. Then it is stirred, magnetic stirrer bar, okay, it is stirred and this is closed and then stirring takes place, then your diffusion will start. This is the experimental setup for the transport experiment. Okay. So, the membrane area is 12.5 square centimeter square, small membrane area in the lab scale. So, 3 ml of the samples are drawn from feed and permeate at 4-hour interval for UV analysis. Okay. Then pH and of the feed and permeate are measured every 4 hours using pH meter, because since endosulfan is moving. So, the pH of the feed as well as the receiving phase is keep on changing, need to adjust that. Okay. We have adjusted the pH also, we have done some control experiments without adjusting the pH also. So, transport experiments is carried out for 24 hours, then membrane weight is noted after the experiment again to find out the loss of IL, to see and to understand how effective is this supported ionic liquid membranes. Why we have chosen ionic liquid? Basically they are green solvents. Okay. Second thing is that they are highly viscous. So, if the liquid membrane viscosity will be more high or will be higher, then its impregnation inside the porous membrane or the pores of the membrane support will be better. So, that is the idea actually. So, this let us just quickly go through. These are some of the results of the experiments. Basically, you can see that here the concentration, these are the concentration of the feed endosulfan, how it is decreasing in the feed side, and this is how it is increasing in the receiving side. Okay. This is same plotted in a different way. Then with different 0.1 molar sodium hydroxide. Okay. Then this one ammonium hydroxide as using as another stripping phase. Okay. So, variation in endosulfan concentration in feed and strip phase as a function of operating time. So, at time how. Okay. So, we have seen that almost after 24 hours no more change is there. So, we have stopped at 24 hours. So, this is with different stripping solution. You can see that we have ammonium hydroxide, potassium hydroxide, sodium hydroxide 0.1 molar, sodium hydroxide 0.1 molar with feed pH adjusted to 2. So, this particular has given the best separation, more than close to 90% separation. Okay. So, we have used that as the stripping phase. So, this is the mechanism actually how what is happening. So, this is again try to understand this is one type of carrier mediated transport. Okay. You can call it as a facilitated transport here. Okay. Here the ionic liquid groups are behaving as actually a carrier. So, the endosulfan, which is actually negatively charged, when it comes, then this is source bed, it comes and sit here on the membrane and feed interface, then diffuse to the membrane phase and bind to the ionic liquid phase. So, you will get ILH plus EL minus. This is an intermediate complex, and the intermediate complex is not stable. Okay. So, then it is moving in this direction by virtue of the concentration difference. What it comes here at the interface of the receiving phase and the membrane phase. So, by virtue of your concentration difference, it will break and it will remove the endosulfan. The endosulfan will bind to the sodium hydroxide, whatever it present here, and will give you Na plus Es minus. So, it becomes a salt. Okay. Since the molecular weight of this particular component is much higher, there will be no back diffusion. So, back diffusion is been discarded out. Okay. So, I hope you will understand how actually we have carried out the experiment. So, in a nutshell, we can say that aim of this work was to remove endosulfan from aqueous solution using the supported ionic liquid membrane. So, maximum weight loss of the membrane after experiment was 4.4%. Okay. So, we can say that it is favorably stable. So, C4D-MIM PF6 with PVDF is used. PVDF is the support, polyvinyl difluoroethylene porous support was used. Okay. And this particular ionic liquid with 0.1 molar sodium hydroxide gave the highest permeation, that is 87% at pH 2 and 71% at pH 6.5, that means without changing the pH. So, lowest permeation was 55% at pH 10. The influence of pH, effect of initial feed concentration and effect of stirring speed was studied. Stripping agents used is sodium hydroxide, potassium hydroxide and ammonium hydroxide, and best stripping agent was 0.1 m sodium hydroxide. So, I hope you have got a taste of how these liquid membranes were being used experimentally to remove certain compounds. With this I conclude today's lecture. So, mostly it is taken from this Knath and Mulder for liquid membrane. Okay. So, please refer these books, and in the next class we will be discussing about gas separation. So, different types of membranes and modules used for gas separation, how the transport happens inside and during gas separation, and factors that affect gas separation and various applications. So, thank you very much. In case you have any query, please feel free to write to me at kmohanty@iitg.ac.in. Thank you very much.